everyone, my name is Noemi, and today I'll be presenting my research on combining hyper-resolution land surface modeling and SMAP brightness temperature to obtain 30 meters satellite-based soil moisture across the United States. Soil moisture highly varies in space and time, and it's critically important for many agricultural and water resources applications. However, because it highly varies in space and time, it's very hard to infer the soil moisture spatial variability based on only a few sparse in-situ observations. My research mostly focused on how can we improve our understanding of the spatial variability of soil moisture. And to this aim, today I'm going to present my work on how can we combine coarse scales, microwave-based satellite observations, and hyper-resolution modeling to improve the information in our knowledge on the spatial variability of soil moisture at a very fine scales. To do that, my presentation will be organized in three main parts. In the first part, I'm going to present the HydroBlocks model, how it is defined, how we set up the experiment. The second part, I'm going to present how can we combine this coarse scale satellite data and the fine scale model estimates to obtain improved soil moisture observations. And in the third part, I'm going to show some evaluation results of our approach. So, HydroBlocks model. What is HydroBlocks? HydroBlocks is a semi-distributed land surface model that uses the concept of hydrological similarity. How we define a hydrological similarity in HydroBlocks is based on clustering high-resolution drivers of the spatial heterogeneity of the landscape, such as topography, land cover, soil properties, and by clustering these drivers, we are able to identify these areas of hydrological similarity. And by using very fine high-resolution data sets as drivers, we are able to have a model that's capable of simulating the hydrological processes at an effective 30 meters spatial resolution. So what HydroBlock does, it uses NoMP land surface model to solve for the physical and vertical processes at each of the HRUs, and then connect the HRUs via lateral and subsurface flow. By using NoMP model, HydroBlocks allow us to simulate also vegetation dynamics and account for the water, energy, and carbon balance, allows us to estimate the soil moisture dynamics in a hydrologically consistent manner. How did we set up HydroBlocks for this study? I ran the model over the continental United States using 11,300 catchments with around 400 hydrological response units for catchments. So that's a lot of grids being simulated in space. However, not so much, because by using this clustering algorithm, we are allowed to reduce the computational expense of the simulation. So the model was run between 2010 and 2019, where 2010 to 2014 were using for spin-up. No model calibration was performed in this experiment for evaluation and see whether the results of the model could be transferable to different regions or not. As inputs to the model, we used the Princeton climate force, which is a downscale version of an LDAS2, 30 meters elevation data, 30 meters soil property data using the Polaris dataset, also developed here in Princeton, and 30 meters the national land cover dataset. So the high resolution variables were used to also cluster and identify the hydrological response units, but also to parameterize the parameters for NoMP. So using this model and this framework, we are able to simulate the soil moisture processes across the US, as shown in this video simulation here. What we can see is that the model can capture very well the footprint of rainfall events, and as the soil moisture disperses across the landscape and converges to the river valleys and river reaches. If you look very closely, when a rainfall events occur, you can start to see the small streams popping up and then drying down as the soil moisture dries. We're able to capture very different events. Soon you're going to see very large scale events also happening. And also other interesting features, such as the different memory of soil moisture that we can observe depending on the different locations across the landscape, such as the West, with very short and localized rainfall events that dries down very quickly, while most of the East, the rain events tends to take a longer memory times. This simulation really motivated and inspired us to combine this approach with satellite data to actually improve the accuracy of our estimates. So let's take a look on how does this 30-meter soil moisture data looks like at 30 meters resolution and actually field scale. So I have here an example for a couple sites. The first is the Sacramento Bay Area. We can see that the model can capture very well the dynamics differentiate between urban and agriculture areas, wetlands, and irrigation fields. Another example here, very briefly, is the lower Mississippi River basin. And what we observe here is how the soil moisture drastically changed from upperlands to lowlands. All the contribution from the channels and valleys. We can also observe how soil moisture varies across the landscape differently over wet and drying conditions. So here I'm showing for soil moisture over Wilmington, North Carolina, shortly after a rain event, so very wet conditions on September the 5th in 2017, and shortly after 2019, extremely dry conditions with very fast and change in these dynamics, not only in time, but also in space. The patterns change quite a bit. Moving on, my research is how can we use now those simulations and combine them with SMAP brightness temperature. So what we did, we took HydroBlocks simulations and we feed them into a forward radiative transfer model, tau omega radiative transfer model, which is the model that SMAP uses, along with SMAP ancillary data to predict what would be the brightness temperature at 30 meters resolution at each of the clusters. Then we merged, using a spatial Bayesian merging scheme, the SMAP observations, which were in coarse scale, to then obtain a merged brightness temperature, which is fed back again to the backward radiative transfer model to then obtain the 30 meters, what we call here is SMAP-HydroBlocks for SMAP-HydroBlocks, 30 meter soil moisture estimates across the landscape. The methodology for this research was published early this year in Remote Sensing of Environment, so you're happy to take a look in the details over there. For to merge those observations, we use a common approach, a Bayesian merging scheme that uses a Gaussian weighted observation operator to bring the observations from the cluster space to the SMAP space. And then once the simulations are in the same space from the observations, we use those differences as increments and feed back these differences into the model, right? So our merge scheme here is split in roughly two parts, the anomalies and the bias. And what we do is we constrain the contribution of the SMAP anomalies and the contribution of SMAP bias using these two terms that we call here W short and W long. And how do we estimate these two terms? Also, by using this merging scheme as proposed here, we allow to reduce the dimension of the system because the merging here happens at the HRU level instead of every grid cell, which reduces the dimension of the matrices here on those operations from between 300 to 500 times. And that's a huge reduction in computation when we're talking about merging observations. So how did we estimate the W short and W long? So to start off with that, we accounted for the contributions of SMAP into the merging scheme and to define what would be this contribution of SMAP anomaly and SMAP seasonal mean, or here we call bias, to the merging scheme. We iterate different combinations of W long and W short for each of 958 in situ observations across the US. And we were able to identify that depending on the location and the soil types and the characteristics, SMAP would contribute to the merged soil moisture in different manners, as we can show here in this figure, where 0 shows where SMAP didn't contribute to the merged soil moisture, and 1 where SMAP contributed a lot to the merged soil moisture. And what we can see here is that it varies a lot in space. So what we did next is to use this information, the synthetic values that we obtained from in situ observations, and we trained a random forest model to try to predict what would be the contribution of SMAP across the landscape. This model was trained based on ancillary data, but also fine scale of drivers of the landscape heterogeneity, as we were discussing previously. And what we can see here on the two bottom lines now is the predicted map for SMAP seasonal mean contribution and SMAP anomalies contribution. And what we can see is that there are locations where SMAP contributes a lot for the emerging skin, so it does help to improve the emergent soil moisture performance. And there are other locations where SMAP doesn't add much value, especially in terms of the seasonal mean values. So what we did then, we used these predicted maps of SMAP contribution to then constrain our emerging scheme. And now let's look into how does the performance of our results look like. So we split the evaluation in temporal evaluation and spatial evaluation. So here for the temporal evaluation, we also split it between testing sample and training sample. So testing sites were the sites used to identify what was this map contribution. And the testing sites were independent sites that were not used or at least 25 kilometers far from any of the different training sites. And what we can observe here is that the model, the emergent soil moisture, which shown in green, show overall the best accuracy in terms of root mean square error and KGE score, both for the training sites and the testing sites. For the training sites, SMAP-L4 tend to show a little bit better correlation. And by looking to the results, we found out that especially happens at these no-till sites, where perhaps our model is not being able to capture very well the precipitation dynamics happening in there that have high influence on soil moisture as well. But at the testing site, actually hydroblocks tend to show, hydroblocks and the emergent soil moisture tend to show a little bit better statistics. We also look into the same temporal statistics, but now distributed over any space, as well as their differences with comparison to the two base products that we use, which was SMAP-L3 and hydroblocks. And what we show here is that in blue, we show the locations where the emergent soil moisture show improvements over the base products. And in red, it shows the locations where the emergent soil moisture tended to worsen the results. So what we can see here is that overall, our emergent product also improved a lot. Most of the estimates, specifically KGE, which was our target metric. We also calculated the spatial correlation at the time steps that we had at least 6 in-situ observations simultaneously available. We performed this experiment considering all the in-situ observations available at the New York Mesonet site, at the Oklahoma Mesonet site, and all in-situ observations we had across the United States. And we show those results here summarized as a time series on the left, and a summary as a blocks plots on the right. And as we can observe, the model showed in red the tended to show better spatial correlation with respect to this map soil moisture product, but that's expected because of its fine scale. However, what was interesting is that when we combine the emergent soil moisture using the approach that we presented here today, the improvement in spatial correlation is much larger than what we observed solely using the model. So that was very encouraging. In summary, here we presented an approach that allows to take advantage of big data, machine learning, high-performance computing, as well as the concept of hydrological similarity and data merging that the hydrological scientific community has been working on many years so now. By combining all these different aspects, here we are able to come up with an estimate, a satellite-based estimate of soil moisture at very fine scales that we really hope that can able to improve the access of information and decision-making related to soil moisture at a very fine scales. And with that, I would like to thank you for your time.